right, this is our last video in 2.1 of APAB. So we're on page 101, you'll see an alternate form of the derivative of f of x, specifically the derivative evaluated at c. So another way to find the derivative evaluated at c, and I do want to walk you through this visually, is let's say I have some function, right, and I have 2 points essentially. Well, I have 2 points. I have x comma f of x, right? And I have c comma f of c, right? If I want the tangent slope, I need those points to be really close together. So one way to write that is to write as x approaches c, like as x gets so infinitely close to c that it's basically c. So that's what this says. It says the limit as x approaches c of y minus the other y value, so f of x minus f of c, over x minus the other x value, x minus c. So that's another way to write the derivative, but it's not the derivative at any point, it's the derivative at a specific point c. So if I did not ask you to find f prime of x, if instead of asking you to find f prime, I just asked you to find f prime of 2, this would be a way to skip to finding f prime of 2, in theory. So a quick thing to note about this, because it's going to be relevant in a second when we talk about differentiability. By definition, this limit, which is a double-sided limit, unless we're talking at an endpoint, right? We know at endpoints there is no left or right at an endpoint of a function, but assuming we're talking an interior point that is not an endpoint of a function, that by definition, this limit only exists if the left-sided limit, as x approaches c from the left, is equal to the right-sided limit as x approaches c from the right of this function, right, of this whole mess. So if the two of them are not equal, we have a situation where something is called not differentiable, like f of x would not be differentiable at c. So now let's walk through the visual. There's only a handful of ways a graph can be not differentiable. And if you know those handful of ways, then it's pretty easy to spot. Number one, a graph is not differentiable if it is discontinuous. So if there is a vertical asymptote, the graph would not be differentiable right there. If there's a jump, the graph would not be differentiable right there. If there's a hole, the graph would not be differentiable right there. Okay, so that's one. Number two, at any points or cusps. So point is like what you see in an absolute value, right? It's that sharp point on a V, right, that you'd see in an absolute value of x. A cusp kind of looks like the edge of a wave. Now, what I want to point out is that those are not differentiable because of this reason that I wrote down here. See how this slope is clearly a negative and this slope is clearly a positive? Well, that means that the left-sided slope can't equal the right-sided slope. They're clearly not the same number, so not differentiable. Same thing here. See how this slope is clearly a positive and this slope is clearly a negative? Well, that means that this number and this number, the two slopes, slope can't equal the other slope, right? The third place that we see something not being differentiable is in a vertical tangent. We actually addressed this in, I think, example 2, when we talked about the square root of x, but right here, vertical tangent line, the graph would not be differentiable, and that's really it. Now, so again, these are spots where the left and right-sided slopes don't equal each other, discontinuities, and then for this one, when you try to do this, you'd get something where, sorry, that's not what I meant. You'd get something where f prime of that c is a number on top of a 0, which is not allowed to happen, okay? So that's what would happen, and that would be your hint if you did do the math that there was an error there. One other note about differentiability. Differentiability implies continuity, because you can't be differentiable if I had to lift up my pen. So if I tell you, I don't have to say that a function is continuous. If I say that f of x is differentiable for all x, then that implies it must also be continuous for all x, because discontinuity is a deal breaker for taking a derivative, right? You cannot differentiate it at discontinuity. So if I say something is differentiable for all x, that implies that I'm also telling you it is continuous for all x, which is going to matter moving forward, because as we discussed when we did the intermediate value theorem, continuity matters in a lot of the theorems and a lot of the stuff that we use both in this current calculus class and also moving forward. That's it for 2.1.